Welcome to this lecture on advanced electric drives. In the last lecture, we were discussing about the flux estimation scheme, the rotor flux estimation scheme, and we have seen actually there are two methods, two ways to estimate the rotor flux. The first method is the voltage based estimation, and the second method is the current based estimation. So in this lecture, we will be discussing about the current based estimation of rotor flux. Now, primarily in this method, we will be estimating the rotor flux from the currents. Currents means the currents of the stator, and the stator currents, when we are transforming into the DQ, they are IDS and IQS respectively. So, before we start discussing about the estimation, let us derive the necessary equations which will be helpful in estimating the rotor flux. So, we can write down the rotor equations. In stationary reference frame, and the D axis equation is as follows: P psi dr plus IDR RR plus omega SL into psi QR, that's equal to 0. So this equation is basically the D axis equation in the stationary reference frame. So omega SL is the slip speed. Slip speed is omega E minus omega R, the slip speed of the rotor. And similarly, we can have the equation in the Q axis. We can write down P psi QR plus IQR RR minus omega SL psi dr, that's equal to 0. So these are the two equations which will help us in estimating the rotor fluxes, and the rotor fluxes are psi dr and psi QR. So let us do some mathematical rearrangement to these two equations. We have two equations with us. We will first take up the D axis equations and do some mathematical readjustment, and then we will similarly do the same thing for the Q axis equations. So we take this equation, and what we do here is the following. We can just rewrite this equation: IDR RR plus P psi dr plus omega SL psi QR. We will be adding, what we will add here is the following. We will add here RR LM by LR into IDS in the right hand side, RR by LR into LM IDS in the left hand side. So the value will not be changed, and then we will do some adjustment, and what we will do here, we will club these two. And if we club these two, we get the following. What we obtain here is the following: P psi dr plus, we can take here RR by LR common, and if we do that, what we obtain here, LR into IDR plus LM into IDS plus omega SL psi QR, that's equal to RR by LR into LM into IDS. And this equation, we know that the second term, the part of the second term is the rotor flux. So this term will give us psi dr. So we can again rewrite this equation in the following fashion: that P psi dr plus, we can say here Lr by Rr is tau r. So, this is 1 by tau r. Tau r is the rotor time constant into psi dr plus omega SL psi qr, that is equal to Lm by tau r into IDS. So, we can further simplify this, and after simplifying, what we obtain here is the following: P psi dr plus 1 upon tau r into psi dr plus omega r psi qr, that is equal to minus of Lm by tau r into IDS, that is equal to 0. Now, in this previous thing, this will be, since we are taking a stationary reference frame, this omega SL, because omega E is equal to 0, when we take the stationary reference frame, we can say that the reference frame speed is equal to 0. So, since the reference frame speed is equal to 0, the omega SL will be replaced by omega R. So, we have here, that is omega R into psi qr and omega R into psi dr. This will also be omega R here. So, we have omega R in this case, and here also we have this omega R, and here also we have this omega R. So, we have omega R here and we have omega R here, and the rotor speed is a known quantity. So, we can always sense the rotor speed by using a sensor. The rotor speed can be measured by using a speed sensor. So, this is what we have. And similarly, in the q axis, we can rewrite the equation in the following fashion: P psi qr plus 1 by tau r into psi qr minus omega r into psi dr minus of Lm by tau r into psi qs, that is equal to 0. So, these two equations will help us estimate the rotor fluxes, that is psi dr and psi qr in the two axes respectively. And this actually requires a little bit of readjustment. So, if we do a small readjustment here, we will get this equation in the following fashion. This equation will be P psi dr. If you want to evaluate what is P psi dr, that is equal to Lm by tau r into IDS minus 1 by tau r into psi dr minus omega r psi qr, and this equation will give us P psi qr, that is equal to Lm by tau r into psi qs minus 1 by tau r into psi qr plus omega r into psi dr. So, these two equations, if they are simplified, if they are solved, will get respectively psi dr and psi qr. Now, we can show this by means of a simple block diagram. Now, what we will do, we will take these two equations and we will evaluate what is P psi dr and P psi qr, and the integration of P psi dr and P psi qr will be psi dr and psi qr respectively. So, that we can show by means of a block diagram. So, we can show that in form of a block diagram in the following fashion. So, we have the currents, and the current is IDS here. We multiply here Lm by tau r, and then output is P psi dr. and we can use an integrator here, and what we obtain is psi dr. And similarly, for the q axis, we have Lm by tau r, and then we have IQS plus here, and we integrate this. This is P psi QR. What we obtain here is psi QR. So these are the two fluxes that we are talking about, but we have some other terms here. As per the equation, we have to complete the equation in the block diagram. So here we have a feedback, and this is 1 by tau r, and we feed back this flux. This is negative here, and similarly in this case we also have a feedback, and we have 1 by tau r. We feed back this flux, and this is negative. The feedback is again negative here. And then we have another term, that is omega r, and the omega r term can be obtained in the following fashion. So we have two multipliers. These are the outputs of the estimator, and the two multipliers are supplied from the speed. The speed can be measured. We can obviously have an encoder to measure the speed. We can have a tacho generator to measure the speed. There are so many speed measuring devices. Encoders, it is quite common for measuring speed for a vector control drive. So we can use an encoder to find out the speed, and this speed can be fed back here. So we can use the speed in this case, and then this is multiplied with psi dr, and this is fed here, right? And similarly, we can multiply here psi qr, and we can feed this here. This is the output in this case. This is also the output, and this feedback is negative here, and this feedback is positive here. So we have a negative feedback in this case, we have a positive feedback here. So this is as per the equation. So this is the current based estimator of the flux. So what we are evaluating here is psi dr and psi qr, and from psi dr and psi qr we can get the information about the flux angle, that is theta e. So how do you obtain theta e? Theta e can be obtained by taking tan inverse of psi qr by psi dr. And please remember, these are basically fluxes in the stationary reference frame. These fluxes will be alternating in nature. They will be a function of time. If you see, this flux is also varying with time. This flux is also varying with time. So you know that these two fluxes are function of time. And if you take tan inverse of this, you will get the information about the flux angle, the angle of the flux vector. Now when we simulate it, there is a function called a tan 2. When we are simulating maybe in MATLAB or in C, this particular to find out this angle, tan inverse is sometimes is not preferred. So what we do here is this: we use a tan 2, a tan 2 psi qr, comma psi dr. Now why do we use a tan 2? Because the flux can be in any of the four quadrants. We have four quadrants here, and we have a flux which is rotating, that is psi r, and this is our angle, that is theta e. This is the angle of the flux vector. The flux can be in any of the four quadrants, and the component of these fluxes like psi dr and psi qr can be positive, can be negative. So to find out the angle in any four quadrant, we have to take the help of a tan 2. If both are negative, they are in the third quadrant. If suppose psi dr is positive, but psi qr is negative, it is in the fourth quadrant, and so on. So, this is the current based estimator. And this depends upon IDS and IQS, and in the previous lecture we have already explained how we can find out IDS and IQS from the currents IA, IB, IC. So, we have the actual currents of the machine, we can use some sensors, and the sensors are commonly Hall effect sensors. We can use the Hall effect sensors to measure IA, IB, IC, and this IA, IB, IC can be transformed into IDS and IQS, and IDS and IQS are the stationary reference currents, and we can use those IDS and IQS here. So, we do not have to integrate the voltage. Since we do not have to integrate the voltage, this estimator works well also at low speed condition. The integration does not depend upon the voltage. So, even at 0 speed, this estimator is going to give us correct result. Okay. So, in many situations we prefer current based estimation to voltage based estimation for this region, that we avoid the integration of the voltage, which becomes very low at low speed condition. So, we will discuss about the vector control fed from a voltage source inverter. We have already seen that we have to use an inverter to inject the currents, and the currents are the physical currents of the 3 phases, and the currents are IA, IB, IC of the 3 phase machine. And to do that, commonly we use voltage source inverter, because voltage source inverter can be easily fabricated, but we need to inject current IA, IB, IC, and hence we have to operate the voltage source inverter in current control mode. Vector control of induction motor from a VSI. Okay. So, what is the conventional practice? Conventional control is operating the voltage source inverter in current control mode. And one of the ways to have current control is the hysteresis current control, that we have already seen, that what we have a reference current, and we can track the reference current within a band. So, one of the ways is to go for hysteresis current control. And in this case, what we do here is that, suppose this is our reference current which has to be tracked, this for phase A. Similarly, we can have for phase B and C. We control the actual current within a band. So, this is how the tracking takes place. So, the actual current tracks the reference current within a hysteresis band. So, we can define a hysteresis band here. We can have an upper band and we can also have a lower band, and actual current is confined within these 2 bands. And this method is quite popular, also conventionally used, but one of the drawbacks of this method is that the switching frequency is variable. When we go for hysteresis current control, the switching frequency of the inverter does not remain constant, and we do not know what is the switching frequency. It actually depends upon various parameters like the decoupling voltage, the parameters of the machine, and so on. So, it can be as low as a few hundreds of hertz, it can be as high as few kilohertz. So, the switching frequency continuously varies as the actual current tracks the reference current. Now, this is one of the drawbacks of this method, that the switching frequency is not known. Now, if we want to operate the inverter on the constant switching frequency mode, what we do, we operate the inverter not as a current controlled VSI, but as a VSI. So, this is called a current controlled VSI. All right. So, we can go for voltage mode control. Now, in the previous one, the drawback is variable switching frequency. Now, in the voltage mode control, the switching frequency can be maintained constant. So, we can operate the inverter like a true VSI, and we can go for constant switching frequency operation. Now, to be able to do that, we have to convert the currents into the voltage, because you know that the vector controller will be giving us IDS and IQS. IDS is the flux component of current, IQS is the torque component of current. So, we have to convert these two currents into the voltages VA, VB and VC. Okay. So, we will see that how this is done. So, what we have, we are talking about a rotor flux orientation, vector control, from a VSI with voltage mode control. So, we are operating this with voltage mode control. Please remember that it is not only true for VSI, it can also be for a cycloconverter. Say for example, if we want to feed an induction motor from a cycloconverter, and the cycloconverter is essentially a voltage fed system. So, we can operate the cycloconverter in voltage control mode and use this technique to have vector control. So, let us see how this is implemented. So, we derive some equations here. So, we take synchronously rotating reference frame, and here what we do, we take the rotor flux orientation, and the equations are pretty straightforward. So, we can write down the equations for the voltage. VDSE is equal to RS IDSE plus P psi DSE minus omega E into psi QSE, and we can simplify this. That's equal to RS IDSE plus, we can replace this psi DSE by the currents LS IDSE plus LM into IDR minus of omega E into, again we can replace this psi QSE by its currents LS IQSE plus LM into IQRE. And we know that IDR equal to psi DR minus LM into IDS by LR, and similarly we can say that IQR is equal to psi QR minus LM into IQS by LR. So, these are the known equations which we can obtain from the flux linkages, and we know that in a vector control drive, which is rotor flux orientation, psi QR equal to 0. So, we can say that this quantity is equal to 0, because this does not exist in a rotor flux oriented vector control drive. Now, if that is equal to 0, we can say that IQR equal to minus of Lm by Lr into IQAC. So what we will do now, we will substitute for IDR and IQR in the previous equation and simplify. And if you substitute that, what we obtain is the following, that VDSE is equal to RS IDSE plus P, this is LS minus Lm square by Lr into IDSE plus Lm by Lr P psi dr E minus omega E into Ls IQAC minus Lm square by Lr into IQAC. And this can further be simplified in the following fashion, that VDSE is equal to RS plus sigma LSP into IDSE plus Lm by Lr P psi dr E minus omega E sigma Ls IQAC. Now this equation is basically the equation for the voltage. So we are able to find out VDS from IDS and IQS. Now sigma is called the leakage factor. Sigma is called the leakage factor, and that's equal to 1 minus Lm square by Ls into Lr. Lm is the magnetizing inductance, and Ls and Lr are the self inductances of the stator and the rotor respectively. Now if the coupling is 100%, suppose we have a very tight coupling between the stator and the rotor, so we can say that Lm square is equal to Ls into Lr. So if there is tight coupling, the leakage factor will be equal to 0. So it means if there is no leakage, sigma is equal to 0. So this basically this is a measure of the leakage inductance of an induction machine, and hence it is called the leakage factor. Now similarly in the Q axis, we can rewrite this equation, VQSE is equal to RS plus sigma LSP into IQAC plus we can have here omega E sigma Ls into IDSE plus omega E into Lm by Lr into psi dre. So this is the equation for the voltage in the Q axis. So we have the equation for the D axis and equation for the Q axis voltage. So it means if we know IDS and IQS or IDAC and IQAC, we can evaluate what is VDAC and VQAC, and which you can show in the form of block diagram. So this basically will translate the currents into the voltages, which will be useful for controlling a voltage source inverter in the voltage control mode. So we will see how we can have that in the form of a block diagram. So this is shown in the following fashion. So we have two summers here. This is RS plus sigma LSP, and we have IDSE here, and then what we have in this case Lm by Lrp, this goes here, and this is psi dre, and what we obtain here is VDSE. And we have some multipliers also here. We have another multiplier here, and what we are feeding in the multiplier, one of the variables is omega e. Omega e can be measured because omega e is the synchronous speed which can be obtained by adding the rotor speed and the slip speed. Okay. So this is fed here, and we have some gain block here, sigma into Ls, as per the previous equation. Then what we have here is IQAC. As we have in the d axis, similarly we can have in the q axis. Here this is for the q axis, Rs plus sigma LSP, and this is our IQAC. This is positive here, this is also positive, and here we have another multiplier, and as we have sigma into Ls here, similarly we have here sigma into Ls, it goes here, and this quantity is IDSC. And here also we have another multiplier, and one of these inputs is omega e, and here we have Lm by Lr is feeding here, and here this is psi dre, and this output is VQSE, and this is positive. So this is actually the complete block diagram which shows how we can evaluate the voltages from the currents. You know that these are available to us. We know IDSC, the flux component of current. We know IQAC, the torque component of current. We of course know psi dr is the rotor flux in the d axis, which is basically the total rotor flux that we know, because psi qr equal to 0, that we know. So this flux is also one of the inputs here, and of course this synchronous speed can be evaluated by adding the rotor speed with the slip speed, omega SL plus omega r. So in a way we know omega e, and then when we use this we obtain VDSC and VQAC, which will be used for a VSI. So what we can say here is that to the transformation block, which will be giving us VA star, VB star and VC star, and once we obtain VA star, VB star and VC star, which are the reference voltages of the three phases A, B and C respectively, we can use an inverter to control the various voltages of the three phases, and we can also operate the inverter at a constant switching frequency. Now we will be discussing about the air gap flux oriented vector control. We have already seen that vector control can be done with respect to the rotor flux vector. It means the d axis of the reference frame is oriented along the rotor flux vector. Now we have so many flux vectors in an induction machine. We can have rotor flux vector, we can have air gap flux vector, we can also have stator flux vector. So it is not mandatory that always we have to go for field orientation with respect to the rotor flux vector. It can always be done with respect to other flux vectors. Say for example, it can also be done with respect to air gap flux vector. Now what is the motivation? The motivation is this, that when we talk about air gap flux vector, air gap flux is easily available compared to the rotor flux. So, in this lecture, we will also discuss about the air gap flux oriented vector control. So, one of the motivations that I have already said, that air gap flux is easily measurable compared to the rotor flux. The rotor flux is inside the machine, inside the rotor. We cannot have any sensor to measure the rotor flux directly. But however, for the air gap flux, we can have some sensors in the air gap to measure the air gap flux, and hence the air gap flux vector is more easily available than rotor flux. So, the air gap flux is easily available compared to rotor flux. So, we can find out the corresponding air gap flux angle to have the transformation. When we are doing the transformation, we have to use the angle of the transformation. Here what we do, we track the air gap flux vector. Suppose this is the air gap flux vector, and we can call this to be psi m. And what we do here, we take a rotating reference frame, and the d axis of the rotating reference frame is oriented along the air gap flux vector. So, we can have the d axis aligned along this vector. This is my d axis, and the q axis is oriented right angle to this. This is the q axis. So, the air gap flux vector is rotating at the speed of omega e superscript m, because we use this omega e to show the speed of the rotor flux vector, and in this case we are talking about the air gap flux vector. So, we use a superscript omega e m, and this we can call as d m and q m to symbolize that this reference frame is a special reference frame where the d axis of the reference frame is aligned along the air gap flux vector. So, we have the stationary phases. The stationary phase is here. This is a reference phase, and this angle that we have here is theta e m. So, what we do here is that we have to find out theta e m, and if we know theta e m, we can transform the variables in the air gap flux reference frame to the stationary A, B, C. We have phase A here, maybe phase B 120 degree phase away from this, phase C 240 degree away from phase A, and hence if we know the angle theta e m, we can evaluate IA, IB, IC in the actual phase variables of the induction machine. So, let us see the torque equation. Now, we know that the torque of an induction machine is given as 3 by 2 into P by 2. If you see the original equation, what we used for the rotor flux orientation was psi dr into, there was a constant here, and the constant is Lm by Lr, into psi dr IQS minus psi qr IDS. Now, this was the equation that we used for rotor flux oriented vector control. Now, if we simplify this equation, we can also derive this equation in the following fashion. If we simplify this, we can have 3 by 2 P by 2 psi ds into IQ. This is a matter of rearrangement. Psi ds into IQS minus psi qs into IDS. So, what we do? We replaced psi dr and psi qr by psi ds and psi qr respectively. So, this torque equation is in terms of the stator flux and the stator currents. Further simplification can give us the following equation. We can say that this is 3 by 2 into P by 2 into psi dm into IQS minus psi qm into IDS, and psi dm and psi qm are the air gap fluxes in the d axis and the q axis respectively. So what we mean here is that this flux in this axis is called psi dm and this is called psi qm. And furthermore, you know that this reference frame is rotating synchronously with the air gap flux vector. So we add a superscript here. We can say that that's equal to psi d m and psi q m, and the currents will be IQS m and IDS m. The superscript m shows that these are special variables. These variables are all defined in a hypothetical reference frame rotating with the air gap flux vector. Of course, when we are talking about the dq axis, remember that the dq axis is in mind. It is basically a hypothetical situation that we are talking about a d axis and a q axis, which are actually non-existent. But these are useful for understanding the control. So this reference frame d and q are the reference frame which is attached to the air gap flux vector, that is psi m. So we symbolize this by using a superscript, that is m. So when we orient the d axis along the air gap flux vector, we can very well say that psi qm m is equal to 0. Because of the special choice of the reference frame, we don't have any q axis flux. So it means this flux is equal to 0. So we can say this flux doesn't exist. And what about psi dm? Psi dm is equal to psi m. The total air gap flux is oriented along the d axis. So we can say that psi dm superscript m is equal to psi m. So in this case, this equation, this will be equal to 0. So what we can say here, that's equal to 3 by 2 into p by 2 into psi dm into psi qsm. So this equation is also a very simple equation, in the sense that if we remember the equation of a DC machine, that the torque is a product of flux and current, or the torque is a product of two currents, this is a simple product of a flux and a current. So it means an induction machine torque equation is similar to that of a DC machine torque equation, even when we are talking about air gap flux orientation. But it is not as simple as rotor flux orientation. We will see a little later that in air gap flux orientation, we don't have inherent decoupling. That we will see when we derive the equations. So what we have right now is the following, that we can write down the rotor equations. And this we are writing all in the air gap flux reference frame. So we can write down in the d axis, the equation is as follows. We have VDR equal to 0, so we can say 0 equal to RR IDR M plus P psi dr M minus of omega SL into psi QR M. This omega SL is again the slip speed with respect to the air gap flux vector. So this is the equation that is coming from the rotor d axis, but this needs some simplification. Now we can simplify as follows. What we can do here is the following, that we can take this equation and instead of writing in terms of the rotor flux, we write in terms of the air gap flux. So we have psi dm M plus LR into IDR M minus omega SL, and psi QRM we can replace by psi QM M plus LR IQRM. So this is actually directly coming from the previous equation, and here we know that this flux is 0. So this flux doesn't exist. So if this flux is 0, we can further rewrite this equation in the following fashion, and before that what we will do here is the following. We will try to replace for psi dr and psi qr. So what we will do here, we can find out the expression for idr and iqr. So psi dm equal to Lm into IDS m plus IDR m, or we can say that IDR is equal to psi dm by Lm minus IDS. In a similar way, we can say that psi qm is equal to Lm IQSM plus IQRM, that is equal to 0, because there is no q axis root flux. So, or we can say here IQRM is equal to minus of IQSM. So, we have been able to find out the expression for IDM and IQM respectively. So, this is our IDRM and this is our IQRM. So, we can eliminate these two variables from the equation, from the d axis equation. So, if we eliminate these variables, we have got the following result. So, after we simplify this, what we obtain here is the following: P psi dm is equal to minus of RR by LR into psi dm plus Lm by LR RR plus LLRP IDSM minus of omega SL into LLR Lm by LR into IQSM. Now, here one interesting thing has to be observed. This equation shows that there is a coupling between IDS and of course IQS and the flux linkage. Say for example, in this case you know that we want to keep the flux constant. This is the flux, and to keep the flux constant we can keep IDS constant. So, this shows a coupling between the d and q axis. So, if we change the torque, that is IQS, IQS is the torque component of current. Suppose I would like to change the torque component of current. Now, if I change this, automatically even if I keep IDS constant, psi dm will be affected. It means what we can say here, that IQSM is coupled to psi dmm. So, this is a very interesting situation where you know that IQS is coupled with psi ds. It means I have one current in the q axis and I have one flux in the d axis. They are orthogonal to each other. Although they are orthogonal to each other, they are coupled. We normally understand that suppose we have two vectors. If I have one vector in the x axis and other vector in the y axis, these two vectors should be normally non-interfering to each other. They should be decoupled from each other. But in this case, although they are two different components in the d and q axis respectively, variation of psi qs in the q axis affects psi dm in the d axis, and hence these two are coupled. It means I cannot independently control the torque and the flux. When I want to control the torque, the flux will be affected, and if the flux is affected, the flux will be delayed, the torque response is also delayed. So, this is basically one of the drawbacks of having air gap flux orientation, but however, this coupling has to be cancelled. If you have a decoupling network, the so-called coupling that is present between the torque and the flux can be eliminated. Okay. So, if you simplify it further, what we have here is the following. Say we can have IDS can be expressed in the following fashion: 1 plus tau LRP into 1 plus tau RP psi dm by Lm plus omega SL tau LR into IQSM. Okay. And here tau LR is the leakage time constant of the rotor, that is equal to LR by RR, and tau R is the time constant of the rotor, that is LR by RR. It means if I want to keep my flux constant, I have to change IDS as per this equation, and if I change IDS as per this equation, IDS can no longer be constant when IQS is changing. If I want to keep the flux constant, say for example, if I want to keep this constant, let us say I have to change IDS with IQS and slip speed. This is reflected from this equation. And similarly, what we can do, we can have the equation in the q axis. We can write down the following equation: 0 equal to RR IQR plus P IQRM into LR plus omega SL into psi dm plus LLR into IDRM. And from this we can obtain the expression for the slip speed, that is equal to 1 by tau R into 1 plus tau LRP into IQSM divided by psi dm by Lm minus tau LR by tau R into IDSM. So, this is the expression for the slip speed, and the expression for the slip speed is little more complicated than compared to rotor flux oriented induction motor drive. Now, here the slip speed contains the derivative terms like tau LRP, and this also has got psi dm, IDSM. Of course, this is again depend upon the parameters like Lm and tau R. Okay, and this slip speed has to be evaluated, because when we evaluate slip speed, we can find out the speed of the air gap flux vector. So, when we obtain slip speed, we can find out omega E. Now, here omega E m, that is equal to the slip speed plus the rotor speed, and once we know omega E m, theta E m, the angle of the rotor, air gap flux vector, can be evaluated by integrating omega E dt. So, in the next lecture, we will try to see that how we can have this decoupling network to cancel the decoupling which is existing in case of an air gap flux oriented vector control.